Listening practice, detailed expansion of Chapter 1, Introduction to Steel Structures, structured for an undergraduate engineering textbook, Chapter 1, Introduction to Steel Structures 1.1 Advantages of Steel Construction Key Benefits, High Strength-to-Weight Ratio, enables long spans and tall buildings. Ductility, absorbs energy in seismic events, versus brittle materials. Speed of construction, prefabrication and rapid erection. Sustainability, 90% plus recyclability, compatible with circular economy. Comparative analysis, property steel concrete timber strength, MPa, 250 to 550 20 to 50 20 to 50 construction speed fast slow moderate fire resistance requires protection inherent combustible 1.2 material properties of structural steel A stress strain behavior, elastic range, /, E equals 200 / GPa, yield point, / sigma _y / strain hardening. Ductility metrics, percent elongation at fracture, typically 15 to 25%. B grades of steel, standard grade yield stress, MPa, applications ASTM A36 250 general construction ASTM A992 345 beams/columns and 10025 S460 460 high-rise buildings. See temperature effects, cold temperatures, increased brittleness, Charpy-Binach testing. Fire conditions, strength loss at 600 degrees Celsius, protection methods, spray, intumescent coatings. 1.3 Steel production and section manufacturing. A production process, 1 iron making, blast furnace pig iron. 2 steel making, BA/EAF roots raw steel. 3 continuous casting, slabs, blooms, billets. B section types, hot rolled, I-beams, W shapes, channels, C sections, angles, L sections. Cold formed, light gauge studs, purlins, thickness 6 mm. Built up, plate girders, box sections for heavy loads. C quality control, mill test certificates, chemical composition, mechanical properties. Non-destructive testing, UT, RT. 1.4 Design philosophies. A allowable stress design, ASD, // sigma _ allow equals / frac / sigma _ YFS FS equals 1.5 to 1.67, limitation, overly conservative for combined loads. B load and resistance factor design, LRFD, / phi r _ n / gic / sum / gamma _ iq _ i / equals resistance factor, 0.9 for bending. / gamma _ i / equals load factors, 1.2 dL plus 1.6 LL. Advantage, probabilistic safety margins. C limit state design, LSD, ULS, strength, buckling, and SLS, deflection, vibration. Eurocode 3, partial safety factors, / gamma _ M0 equals 1.0 / gamma _ M1 equals 1.1 / 1.5 Case study, steel versus concrete decision project, 30-story office tower. Steel solution, 8% faster construction earlier ROI. 15% lighter reduced foundation costs. Concrete solution, lower floor vibrations. Better fire resistance without additional protection. Chapter summary, steel's versatility stems from its strength, ductility, and prefabrication potential. Material selection balances cost, performance, and sustainability. Modern codes, AISC, Eurocode, use limit state approaches for efficiency. Review questions 1. Calculate the weight savings using A992 steel, sigma underscore y equals 345 MPa, versus A36, sigma underscore y equals 250 MPa, for a W12X50 beam. 2. Why does LRFD often result in lighter sections than ASD? 3. Identify 3 NDT methods for steel quality assurance. Practice problems. Basic. Compare the cross-sectional area needed for a 500 knots tension member using ASD versus LRFD. Advanced. Research and summarize the environmental impacts of EAF versus Boss steel production. Key pedagogical features. Industry data, ASTM/Eurocode comparisons. Visual aids, stress-strain curves, rolling mill diagrams. Decision-making focus, steel-concrete trade-off analysis. Suggested additions, video link, virtual tour of a steel mill. Software, demo of section property calculators, e.g., AISC Steel Toolkit. Would you like to include historical evolution, e.g., Eiffel Tower's wrought iron to modern HSLA steel, or focus on current practices? Chapter 2, Design Loads and Codes. 2.1 Types of loads on steel structures. A. Dead loads, DL, definition, permanent static forces, self-weight and fixed attachments. Examples, steel member self-weight, use AISC Manual Table 1-1, concrete slabs, 24 kN/m superscript 3 times thickness, cladding, 0.5 1.5 kN/m superscript 2b. Live loads, LL, categories, floor LL, office, 2.4 4.8 kN/m superscript 2, retail, 4.8 7.2 kN/m superscript 2, roof LL, 0.96 kN/m superscript 2, ASCE 7, dynamic loads, e.g., forklift, 1.25 times static weight, see environmental loads. Load type. Key parameters. Design standard wind basic speed, e.g., 140 miles per hour, exposure category ASCE 7 CH26 seismic S, site class ASCE 7 CH11 snow ground load roof load, PGPF, ASCE 7 CH7 special loads, crane runway, impact factor equals 25%, blast loads, UFC 4-010-01, 2.2 load combinations AASCE 7 to 22 LRFD combinations 1/1.4 DL 2 1.2 DL plus 1.6 LL plus 0.5 L underscore R or S or R, 3 1.2 DL plus 1.6 L underscore R or S or R, plus 0.5 LL or 0.8 W, 4 1.2 DL plus 1.0 W plus 0.5 LL plus 0.5 L underscore R or S or R, 5 1.2 DL plus 1.0 E plus 0.5 LL plus 0.2 S B Eurocode and 1990 combinations, fundamental, 1.35 DL plus 1.5 LL plus 0.6 W seismic, DL plus 0.3 LL and E critical combination selection, for beams, typically 1.2 DL plus 1.6 LL for columns, often 1.2 DL plus 1.0 E plus 0.5 LL -2.3 Design Codes Overview AAISC 360-22, USA, Chapters, B, Tension Members, F, Flexural Design, H, HSS Connections, Notable Provisions, Shear Lag Factor, U for Tension Members, C underscore B factor for LTBB Eurocode 3, N. January 1, 1993, Key Differences versus AISC, Partial safety factors, backslash gamma underscore m0 equals 1.0 backslash gamma underscore m1 equals 1.1 section class 4 requires effective width calc C. Other codes, is 800, India working stress plus limit state, GB 50017, China similar to Eurocode with local adaptations. 2.4 Practical application, warehouse design given, location, Chicago, wind, 115 miles per hour, seismic, S equals 0.25 G, loads, DL equals 2 kN/m superscript 2, LL equals 6 kN/m superscript 2, snow equals 1.2 kN/m superscript 2. Step by step, 1. Calculate wind pressure, backslash, Q underscore Z equals 0.613 K underscore Z K underscore Z K underscore DV2 backslash, ASCE 7 EQ 26.10 to 1, 2. Critical combo, backslash, 1.2 DL plus 1.6 LL plus 0.5 S backslash, 3. Select code, AISC 360 Chap BF Chapter Tools Quick REF Table, Code Tension Design Bending Check AISC backslash phi underscore TP underscore N equals 0.9 F underscore Y underscore G backslash phi underscore BM underscore N equals C underscore B, Z underscore XF underscore Y, backslash, EC3 backslash, N underscore TRD equals A underscore EFFF underscore Y backslash gamma underscore M0 backslash, M underscore CRD equals W underscore PLF underscore Y backslash gamma underscore M0 backslash, flowchart, load combination selection process review questions 1. Compute the factored load for a roof with DL equals 3 kN/m superscript 2, LL equals 1.5 kN/m superscript 2, and S equals 1.8 kN/m superscript 2 using ASCE 7. 2. Why does Eurocode use backslash gamma underscore M0 equals 1.0 for cross-section resistance? 3. Compare wind load calcs per ASCE 7 versus N January 4, 1991 for a 50m tall building. Design exercises, basic, design a tension member for 400 knots, AISC versus EC3. Advanced, optimize column size for backslash, 1.2 DL plus 1.6 LL plus 0.8 W backslash, combo. Key features, code comparative, direct AISC/Eurocode equation comparisons, visual load paths, diagrams showing how loads transfer to foundations, digital integration, links to ASCE 7 online load calculators, suggested add-ons, Excel template for automated load combinations, case study on September 11 WTC collapse, load redistribution lessons. Would you like workshop examples, e.g., connection design per AISC 360 CHJ, or more focus on seismic detailing? Chapter 3, Steel Section Properties and Classification 3.1 Standard Rolled Sections. A hot rolled shapes, ASTM A6, Section Type Designation. Key Properties. Typical uses wide flange, W 12 times 50 A equals 14.6 in superscript 2, 9 equals 391 in beams, columns. Channel, C 9 times 20 A equals 5.87 in superscript 2, 9 equals 60.9 in purlins, bracing angle, L 4 times 1/2 A equals 3.75 in superscript 2, RZ equals 0.78 in truss members. B metric equivalents, N 10,025, He. Sections, e.g., HE300A, H equals 290 mm, B equals 300 mm, UPE channels, e.g., UPE 200, H equals 200 mm, C section property calculations, moment of inertia, backslash, I underscore X equals backslash int Y2 da backslash, elastic section modulus, backslash, S underscore X equals I underscore X slash Y underscore max backslash, plastic modulus, backslash, Z underscore X equals A slash 2 times, Y underscore 1 plus Y underscore 2, backslash, 3.2 built up sections A common configurations 1. Plate girders, web, 5/16 to 1/2 thick, flange, 1 to 3 thick, proportioning, backslash, H slash T underscore W less than or equal to 335 slash backslash SQRTF underscore Y backslash, AISC, 2. Box sections, typical sizes, 12 times 12 to 36 times 36, stiffener requirements per AISC J10B design considerations, weld shrinkage effects, local buckling prevention, cost comparison versus rolled sections 3.3 section classification AAISC 360 classification class flange criteria web criteria design strength compact backslash B underscore F slash 2T underscore F less than or equal to 0.38 backslash SQRTE slash F underscore Y backslash H slash T underscore W less than or equal to 3.76 backslash SQRTE slash F underscore Y backslash, full plastic capacity. Non-compact exceeds compact but less than or equal to backslash, 1.0 backslash SQRTE slash F underscore Y backslash, yield moment slender exceeds non-compact limits effective section B Eurocode 3 classification, class 1, plastic hinge rotation capacity, class 2, moment redistribution, class 3, elastic design, class 4, effective width method see practical examples 1. W14 times 90, A992 steel, flange, backslash, B underscore F slash 2T underscore F equals 7.7 backslash, versus backslash, lambda underscore P equals 9.15 backslash, compact, web, backslash, H slash T underscore W equals 25.9 backslash, versus backslash, lambda underscore P equals 90.5 backslash, compact 2. Built up section, check flange, backslash, B slash T less than or equal to 0.56 backslash SQRTE slash F underscore Y backslash, check web, backslash, H slash T underscore W less than or equal to 1.49 backslash SQRTE slash F underscore Y backslash, 3.4 section selection methodology A flowchart for engineers 1. Determine loading conditions 2. Calculate required section modulus 3. Select trial section from AISC Manual 4. Verify classification and capacity B optimization techniques, weight versus depth trade-offs, serviceability considerations, deflection limits, chapter tools quick reference tables, compactness limits for common steels, A36, A572, A992, section modulus ranges for standard sections case study, comparison of W section versus built-up girder for 60 span review questions 1. Determine the class of W18 times 35, A992, for bending about x-axis 2. Calculate required flange thickness to maintain compactness for given width 3. Compare plastic moments for compact versus non-compact sections design exercises, basic, select lightest W section for given moment capacity, advanced, design built-up section to replace W24 times 94 key features, visual comparison, side-by-side section property charts, code-aligned, AISC/Eurocode classification criteria, practical focus, real-world section selection examples suggested add-ons, interactive section property calculator, BIM integration for automated section selection. Would you like more emphasis on composite section design or cold-formed steel sections? Chapter 4, Tension Members 4.1 Introduction to Tension Members Applications, Truss Members, Bracing Systems, Suspension Bridge Cables, Industrial Hangers and Ties Behavior under Load, Elongation governed by backslash delta equals frac PLAE backslash, Failure Modes, Yielding, Fracture, block shear 4.2 designed for yielding and fracture. A yielding in gross section, AISC 360D2, design strength, // phi TP _N equals 0.9 F _YA _G /quad /text, LRFD, // P _ N /Omega T equals /frac F _YA G 1.67 A G gross cross-sectional area /quad /text, ASD, B fracture in net section, AISC 360D3, effective net area, /A _E equals UA _N /U shear lag factor, table D 3.1, /A _N net area, deducting bolt holes, design strength, // phi TP _N equals 0.75 F UA E quad text, LRFD, frac P _ N Omega T equals frac F UA E 2.0 quad text, ASD, worked example, determine tensile capacity of AC 6 times 13 channel with A _G equals 3.81 text into F _Y equals 50 text KSI F _U equals 65 text KSI and 2/3 in bolt holes. 4.3 Block shear failure. A mechanism, combination of tensile rupture on one plane and shear yielding / rupture on perpendicular plane. BAISC 360J 4.3 equations, // phi R _ N equals // phi left, 0.6 F UA NV plus U BS F UA NT right, lec phi left, 0.6 F YA GV plus U BS F UA NT right, A NV net shear area, A NT net tension area, U BS equals 1.0 uniform stress. Worked example, calculate block shear capacity for a tension member with staggered bolts. 4.4 Design of rods, bars, and cables. A threaded rods, A36/A449, design for net tensile area, table 7-18 in AISC manual, turnbuckle applications. B flat bars, check slenderness ratio / frac LR lec 300 AISC D1, C steel cables, breaking strength, typically 80 to 90% of ultimate strength, corrosion protection, galvanizing or sheathing. 4.5 Practical applications. Case study 1, suspension bridge cable, material, ASDMA 586, high strength strand, corrosion protection, zinc. Coating and HDPE sheathing. Case study 2, industrial bracing, double angle versus single rod comparison. 4.6 Common mistakes, shear lag, ignoring U factor for eccentric connections, net area, forgetting staggered hole deductions, block shear, misidentifying failure planes. Chapter tools. Quick reference, member type critical check governing equation W shape fracture / 0.75 F UA E double angle. Block shear AISC EQJ 4-5 rod thread stripping / 0.75 F UA N flowchart, tension member design process. Review questions. 1. Compute / A E / 4AW 8 times 24 with 1 in bolts at 3 in spacing. 2. Why does block shear require checking both rupture and yielding? 3. Compare LRFD versus ASD safety factors for fracture. Design exercises. Basic, select a double angle member for 200 kip tension, AISC manual table 5 to 8. Advanced, optimize a gusset plate connection to prevent block shear. Key features, failure mode visuals, diagrams of yielding versus fracture versus block shear, code comparison, AISC versus Eurocode tension rules, software integration, Python script for net area calculation, suggested add-ons, video demo of tensile coupon testing, Excel template for block shear calculations. Would you like more connection design examples or fatigue analysis for cyclic loading? Chapter 5, Compression Members, Columns, 5.1 Introduction to Column Behavior. Failure modes, flexural buckling, most common, local buckling, flange/web, torsional buckling, thin-walled open sections, key parameters, slenderness ratio \, \left, \frac KLR \right, critical stress \F_CR, -5.2 Euler buckling theory. A basic equation, \P_CR equals \frac pi2 EI, KL, 2 K effective length factor, valid for \frac KLR 4.71 SQRT \frac EF_Y elastic buckling, B limitations, assumes perfect geometry, neglects residual stresses. Worked example, calculate Euler buckling load for W12 times 65, I_x equals 533 text in 4 with L equals 20 text foot pinned ends. 5.3 Effective length concepts. A theoretical K factors, boundary conditions K pinned 1.0 fixed 0.5 fixed pin 0.7 fixed free 2.0 B practical adjustments. AISC commentary. Fig CA 7.1 for frame buckling, alignment charts for unbraced frame. See lateral bracing impact, unbraced length versus buckling capacity. 5.4 AISC column design curves. A critical stress equations, 1 inelastic buckling \, left, \frac KLR \lec 4.71 SQRT \frac EF_Y right, F_CR equals \left, 0.658 frac F_Y F_E right, F_Y 2. Elastic buckling, F_CR equals 0.877 F_E where F_E equals \frac pi2 E left, \frac KLR right, 2 B design strength, /phi_CP_N equals 0.90 F_CRA_G quad text, LRFD, /frac P_N /omega_C equals /frac F_CRA_G 1.67 quad text, ASD, worked example, determine design strength for W10 times 49, A_G equals 14.4 text in 2 R_Y equals 2.54 text in with KL equals 15 text foot -5.5 Built-up columns and lacing systems. A common configurations, double angles, back-to-back with spacers, laced columns, parallel components with diagonal lacing, battened columns, horizontal battens. B design requirements, AISC E61. Slenderness ratio \, left, \frac LR \right, _EFF \lec 0.75 times governing ratio 2. Lacing bars designed for /2 of axial force. C connection details, minimum bolt spacing, welded versus bolted options. Worked example, design lacing for double angle column, 2L 6 times 4 times 1/2, carrying 500 kips. 5.6 Practical Applications Case Study 1, Mill Building Column, Built-up section with batten plates, Residual stress effects. Case Study 2, High-rise steel column, K-factor determination in moment frame. 5.7 Common mistakes, effective length, ignoring frame buckling effects, local buckling, overlooking flange/web limits, lacing design, underestimating shear forces. Chapter Tools. Quick reference, steel grade / frac KLR / limit / F_CR / equation A992, phi equals 50 ksi, 113 inelastic. A36, phi equals 36 ksi, 134 inelastic. Flowchart, column design process. Review questions. 1. Compute / F_CR / for W14 times 90, / R_Y equals 3.70 / text in / with / KL equals 18 / text foot / 2. Why does AISC use 0.877 multiplier for elastic buckling? 3. Compare laced versus battened column efficiency. Design exercises. Basic, select lightest W12 for 800 kip load, / KL equals 16 / text foot / Advanced, design built-up column with 1200 kip capacity. Key features, buckling visuals, animation of different buckling modes, code comparison, AISC versus Eurocode column curves, spreadsheet tool, critical stress calculator. Suggested add-ons, video of column buckling tests, BIM integration for automatic K-factor determination. Would you like more on seismic column design or composite column methods? Chapter 6, Beams and Bending Members. 6.1 Introduction to Beam Behavior. Key failure modes, flexural yielding, lateral torsional buckling, LTB, web local buckling, WLB, shear yielding / buckling. Design philosophy, strength limit states, ensure adequate capacity, serviceability, limit deflections, e.g., /L/360 / 4 floors. 6.2 Bending strength, yield and plastic moment, a yield moment, /M_Y /M_Y equals F_Y S_X S_X elastic section modulus B plastic moment, /M_P /M_P equals F_Y Z_X plastic section modulus CAISC 360 F2 design strength, compact sections, /phi_B M_N equals 0.90 M_P quad text, LRFD, frac M_N /omega_B equals frac M_P 1.67 quad text, ASD, worked example, calculate M_P for W18 times 50, Z_X equals 101 text in 3 F_Y equals 50 text KSI -6.3 lateral torsional buckling, LTB, A governing equations, AISC 360 F21. Compact sections, L_B lec L_P full plastic capacity, L_P L_B lec L_R inelastic LTB, L_B L_R elastic LTB2. Limiting lengths, L_P equals 1.76 R_Y SQRT frac EF_Y L_R equals /pi R_TS SQRT frac E 0.7 F_Y 3. Nominal strength, /M_N equals C_B left M_P, M underscore P, 0.7 F underscore Y S underscore X, backslash left, backslash frac L underscore B, L underscore P L underscore R, L underscore P backslash right backslash lec M underscore P backslash B moment gradient factor, backslash, C underscore B backslash C underscore B equals backslash frac 12.5 M underscore max 2.5 M underscore max plus 3 M underscore A plus 4 M underscore B plus 3 M underscore C backslash worked example, determine backslash, M underscore N backslash, for W 16 times 31, backslash, L underscore B equals 12 backslash text foot backslash, C underscore B equals 1.14 backslash, dash 6.4 web local buckling, WLB, A slenderness limits, compact web, backslash frac HT underscore W backslash lec 3.76 backslash SQRT backslash frac EF underscore Y backslash, non-compact web, backslash, 3.76 backslash SQRT backslash frac EF underscore Y backslash. Frac HT underscore W backslash lec 5.70 backslash SQRT backslash frac EF underscore Y backslash, B strength reduction, for non-compact webs, backslash M underscore N equals M underscore P, F underscore Y S underscore X, backslash left, backslash frac backslash lambda underscore P backslash lambda underscore R, backslash lambda underscore P backslash right, backslash worked example, check W 14 times 90 web for local buckling, backslash, H slash T underscore W equals 25.9 backslash. Dash 6.5 design for shear A shear yielding, AISC 360 G2 backslash phi underscore VV underscore N equals 1.00 backslash times 0.6 F underscore YA underscore WC underscore V backslash quad backslash text, LRFD, backslash, A underscore W equals DT underscore W backslash, C underscore V equals 1.0 backslash, 4 backslash, H slash T underscore W backslash lec 2.24 backslash SQRT E slash F underscore Y backslash, B shear buckling, tension field action, AISC 360 G3, stiffener requirements worked example, calculate shear capacity for W 12 times 40, backslash, D equals 11.9 backslash text in, T underscore W equals 0.295 backslash text in backslash. Dash 6.6 Practical Applications Case Study 1, Composite Floor Beam, Moment Redistribution with Concrete Slab Case Study 2, Crane Runway Girder, Combined Bending, Shear, and Torsion. Dash 6.7 Common Mistakes, LTB, Ignoring Unbraced Length Effects, Web Crippling, Overlooking Concentrated Loads, Deflection, Neglecting camber requirements. Dash chapter tools quick reference, parameter compact limit non-compact limit dash flange, backslash, B underscore F slash 2T underscore F backslash, 0.38 backslash SQRT E slash F underscore Y backslash, 1.0 backslash SQRT E slash F underscore Y backslash, web backslash, H slash T underscore W backslash, 3.76 backslash SQRT E slash F underscore Y backslash, 5.70 backslash SQRT E slash F underscore Y backslash, flowchart, beam design process dash review questions 1. Compute backslash, M underscore P backslash, for W 21 times 62, backslash, Z underscore X equals 144 backslash text in 3 backslash 2. Why does backslash, C underscore B backslash, affect LTB capacity? 3. Compare shear design per AISC versus Eurocode. Design exercises, basic, select lightest W shape for backslash, M underscore U equals 300 backslash text kip FT backslash, L underscore B equals 10 backslash text foot backslash. Advanced, design stiffeners for concentrated load. Dash key features, failure mode animations, LTB versus WLB visualization, code comparison, AISC versus Eurocode bending rules, spreadsheet tool, C underscore B backslash, calculator suggested add-ons, video of beam collapse tests, BIM integration for automatic unbraced length detection. Would you like more on plate girders or composite beam design? Chapter 7, Combined Loading Members 7.1 Introduction to Beam Columns Definition, Structural members subjected to simultaneous axial compression and bending, uniaxial or biaxial. Common applications, moment frame columns, eccentrically loaded truss members, industrial columns with crane loads. Key challenges, P-delta effect, secondary moments from axial load acting through deflections, P-delta effect, global story drift effects. 7.2 Interaction equations, AISC 360H1, a basic form, frac P underscore U phi underscore C P underscore N plus frac 89 left, frac M underscore UX phi underscore B M underscore NX plus frac M underscore UI phi underscore B M underscore New York right, lec 1.0 quad text, for P underscore U gc 0.2 text, frac P underscore U2 phi underscore C. P underscore N plus left, frac M underscore UX phi underscore B M underscore NX plus frac M underscore UI phi underscore B M underscore New York right, lec 1.0 quad text, for P underscore U 0.2 text, B parameters, P underscore U factored axial load, M underscore UX, M underscore UI factored moments about X and Y axes, P underscore N nominal axial capacity, Chapter 5, M underscore NX, M underscore New York nominal flexural capacity, Chapter 6, worked example, check W12 times 65, P underscore N equals 500 text kips, M underscore NX equals 300 text kip FT under P underscore U equals 200 text kips, M underscore U equals 150 text kip FT -7.3 Biaxial bending cases. A special considerations, weak axis sensitivity, y-axis buckling often governs, torsional effects, warping stresses in open sections. B modified interaction equation, left, frac M underscore UX M underscore NX /right, zeta plus left, frac M underscore UI M underscore New York /right, zeta lec 1.0 zeta equals 1.5 for rectangular sections, M underscore NX equals phi underscore B M underscore NX, 1, P underscore U phi underscore C P underscore New York, worked example, analyze HSS 12 times 8 times 1/2 under P underscore U equals 100 text kips, M underscore UX equals 80 text kip FT, M underscore UI equals 40 text kip FT -7.4 Second order effects. A amplification factors, AISC Appendix 8, B underscore 1 equals frac C underscore M1, alpha P underscore U P underscore E1 gc 1.0 B underscore 2 equals frac 1 alpha some P underscore U some P underscore E2 P underscore E equals pi 2 EI KL 2 Euler buckling load, backslash, C_m moment gradient factor B design procedure, 1 calculate first order moments 2. Apply backslash, B_1 backslash, member, and backslash, B_2 backslash, frame, factors 3. Check interaction equations. 7.5 Practical applications. Case study 1, moment frame corner column, high backslash, P_U/M_U backslash, ratio, bidirectional moment demands. Case study 2, industrial column with crane loads, eccentric vertical and horizontal loads. 7.6 Common mistakes, interaction checks, using wrong equation form, backslash, P_U backslash, threshold, amplification, neglecting backslash, B_2 backslash, in unbraced frames, buckling direction, not checking both axes. Chapter Tools. Quick reference, section. Type critical interaction amplification needed. W shape strong axis bending and axial yes, for backslash, KL/R50 backslash, HSS biaxial bending rarely, torsion resistant, flowchart, beam column design process. Review questions 1. Solve interaction equation for backslash, P_U equals 150 backslash text kips, M_U equals 200 backslash text kip FT backslash, P_N equals 600 backslash text kips, M_N equals 350 backslash text kip FT backslash. 2. Why does backslash, C_M backslash, differ for braced versus unbraced members? 3. When can biaxial effects be neglected? Design exercises, basic, check W14 times 90 under backslash, P_U equals 400 backslash text kips, M_U equals 250 backslash text kip FT backslash. Advanced, design base plate for moment resisting column. Key features, visual aids, interaction diagram 3D plots, software integration, Python script for second order analysis, code comparison, AISC versus Eurocode beam column rules suggested add-ons, video of beam column failure tests, Excel template for automated interaction checks. Would you like more on seismic detailing or composite beam columns? Chapter 8, Bolted connections. 8.1 Bolt types and grades. A common bolt types. Type standard characteristics. Typical use A325 ASTM high strength, heat treated structural steel. A490 ASTM higher strength than A325 heavy construction grade. 8.8 ISO 898 to 1 metric equivalent to A325 global projects. A307 ASTM low carbon, general purpose light structures. B. Bolt grades and strengths. Bolt grade tensile strength, MPa, yield strength, MPa, A325 830 725 A490 1035 910 8.8 800 640 C. Installation methods, snug tight, hand tightened plus partial turn, pretensioned, calibrated wrench or turn of nut, AISC/RCSC, slip critical, high friction for dynamic loads. 8.2 Failure modes. A. Shear failure, single/double shear, /phi r_n equals /phi f_nva_b /quad, /phi equals 0.75, f_nv shear strength, e.g., 400 MPa for A325, B. Bearing failure, on bolt, /phi r_n equals /phi 2.4 dt f_u /quad, /phi equals 0.75, on plate, /phi r_n equals /phi 1.2 L_ct f_u /quad, text for L_c /gic 2d, /c tension failure, bolt fracture, phi r underscore n equals phi f underscore n ta underscore b quad, phi equals 0.75, pull through, requires washer plates worked. Example, calculate shear capacity of a 20 mm A325 bolt in double shear. 8.3 Eccentric connections. A types of eccentricity, in plane, causes shear plus moment, e.g., bracket connections, out of plane, causes torsion, e.g., beam to column connections. B. Elastic analysis method, instantaneous center of rotation, ICR r equals r underscore ULT, 1, e minus 10 delta, 0.55 vector summation, r underscore resultant equals SQRT, sum v underscore I, 2 plus, sum h underscore I, 2 CAISC tables, coefficient method, table 7 to 7 to 7 to 14, C equals function of geometry and load angle worked. Example. Design a bracket connection for 50 knots load at 150 mm eccentricity. 8.4 Practical applications. Case study 1, steel frame moment connection, pretensioned A490 bolts for seismic resistance. Case study 2, truss gusset plate, bolt pattern optimization for combined shear and tension. 8.5 Common mistakes, edge distance, violating minimum 1.5 d requirement, slip critical overuse, applying where not needed, bearing assumptions, ignoring tear out risk. Chapter tools. Quick reference, failure mode governing equation critical parameter shear phi f underscore nva underscore b bolt diameter bearing phi 2.4 dtf underscore u material thickness tension phi f underscore nta underscore b bolt grade flowchart, bolt connection design process. Review questions. 1. Compare A325 versus A490 bolt capacities in shear and tension. 2. Why is the ICR method more accurate than elastic vector analysis? 3. When is slip critical design mandatory? Design exercises. Basic, select bolt size for 100 knots shear load, A325, double shear. Advanced, analyze eccentric connection using ICR method. Key features, failure animations, shear versus bearing versus tension failures, code alignment, AISC 360-16. Chapter J. Provisions, digital tools, Python script for eccentric connection analysis. Suggested add-ons, video of bolt testing, shear/tear out, CAD files for standard bolt patterns. Would you like more on seismic bolt requirements or metric versus imperial comparisons? Chapter 9, Welded connections. 9.1 Weld types and symbols. A common weld types. Weld type AWS symbol characteristics. Applications fillet weld, triangular cross section, general connections, groove weld, full penetration, moment connections, plug/slot weld, fills, pre-drilled holes, lap joints. AWS welding symbols, basic elements, arrow line, reference line, tail. Example, AWS symbol. Example, fillet weld, 6 mm, intermittent 6-50/150 C. Weld quality, inspection methods, visual, VT, ultrasonic, UT, radiographic, RT, defects, porosity, undercut, lack of fusion. 9.2 Fillet and groove weld design. A fillet weld strength, AISC 360J2, // phi r underscore n equals / phi 0.6 f underscore exxa underscore w / quad, / phi equals 0.75, / a underscore w equals / effective throat area / equals 0.707 times text leg size times text length f underscore exx equals / electrode strength, e.g., E70xx, 485 MPa, B groove weld. Strength, full penetration, Phi r underscore n equals Phi f underscore ya underscore g quad, text matches base metal, partial penetration, Phi r underscore n equals Phi 0.6 f underscore exxa underscore eff worked example, design a 200 mm long fillet weld, E70XX, for 150 knots load. 9.3 eccentric welded connections. A elastic vector method 1. Direct shear, f underscore v equals frac pa underscore w 2. Torsional shear, f underscore max equals frac mrj underscore w j underscore w equals polar moment of weld group B. Ultimate strength method, instantaneous center of rotation, ICR r equals r underscore 0, 1, e minus 0.25 delta, 1.5 worked example, analyze a bracket with 100 knots load at 200 mm eccentricity. 9.4 Practical applications. Case study 1, moment connection, CJP groove welds at beam flanges, fillet welds for shear tabs. Case study 2, tube to gusset connection, fillet weld all around. 9.5 Common mistakes, throat versus leg size, confusing 0.707 w with w overwelding, excessive size increases distortion, ignoring eccentricity, treating all loads as concentric. Chapter tools. Quick reference, weld type strength equation critical parameter fillet 0.6 f underscore exxa underscore w throat thickness groove f underscore ya underscore g base metal strength flowchart, weld selection process. Review questions 1. Decipher AWS symbol, 8-100/202. Why is 0.6 f underscore exx used for fillet welds? 3. Compare elastic versus ultimate methods for eccentric welds. Design exercises, basic, size fillet welds for 200 knots shear, E70XX. Advanced, design moment connection with CJP groove welds. Key features, visual guides, weld cross sections, symbol diagrams, code compliance, AWSD 1.1/AISC 360 standards, software integration, weld group calculators, suggested add-ons, video of weld testing, tensile/shear, CAD templates for standard weld details. Would you like more on fatigue design or automated welding robotics? Chapter 10, Special Connections. 10.1 Moment connections, rigid, semi-rigid, A types of moment connections. Type rotation capacity typical details applications rigid, FR, 0.005 rad welded flange plates high-rise frames semi-rigid, PR, 0.005 0.02 rad extended end plates mid-rise buildings simple 0.02 rad double angles secondary systems B design requirements, AISC 358. Pre-qualified connections, reduced beam section, RBS, bolted flange plate, strength criteria, \m underscore PR equals C underscore PRR underscore YF underscore YZ underscore E C underscore PR equals strain hardening factor, 1.0 1.6, worked example, design an RBS connection for W24x94 beam, F underscore Y equals 345 MPa. 10.2 Gusset plate design. A key considerations, Whitmore section, B underscore EFF equals B plus 2L tan 30 degrees block shear, R underscore N equals 0.6 F underscore UA underscore NV plus U underscore BSF underscore UA underscore NT B seismic detailing, compact geometry, avoid abrupt changes, buckling prevention, backslash T underscore min equals backslash frac L 300 backslash SQRT backslash frac F underscore YE backslash worked example, design gusset for diagonal brace, 200 knots tension, A36 steel. 10.3 column splices and base plates. A column splices, location, typically at 4-5 m intervals, design forces, 50% of axial capacity, 25% of moment capacity. B base plate design, AISCDG1, 1. Bearing strength, backslash phi underscore CP underscore P equals backslash phi underscore C 0.85 F underscore CA underscore 1 backslash SQRT backslash frac A underscore 2A underscore 1 backslash 2. Thickness calculation, backslash T underscore min equals M backslash SQRT backslash frac 2P underscore U 0.9 F underscore YBN backslash worked example, design base plate for W14 times 120 column, backslash, P underscore U equals 1500 backslash, KN, backslash, F underscore C equals 30 backslash, MPa. 10.4 Practical Applications Case Study 1, Seismic Moment Frame, RBS Connections with Welded Unreinforced Flanges. Case Study 2, Transmission Tower, Multi-Member Gusset Plates. 10.5 Common Mistakes, Moment Connections, Ignoring Panel Zone Effects, Gusset Plates, Overlooking Buckling Checks, Base Plates, Underestimating Anchor Rod Forces. Chapter Tools. Quick Reference, Connection Governing Code Critical Check Moment, FR, AISC 358 Panel Zone Shear Gusset Plate AISC 341 Whitmore Section Base Plate AISC DG1 Concrete Bearing Flowchart, Connection Type Selection. Review Questions 1. Why are RBS connections preferred in seismic zones? 2. Calculate Whitmore width for gusset with 200 mm attachment. 3. Size base plate for W12 times 65, backslash, P underscore U equals 900 backslash, KN. Design exercises, basic, design bolted flange plate moment connection. Advanced, optimize gusset plate for V-bracing. Key features, detail drawings, standard connection CAD templates, failure case studies, Northridge earthquake lessons, software links, base plate design spreadsheet, suggested add-ons, video of connection testing, cyclic loading, BIM models for standard connections. Would you like more on modular connections or 3D printed nodes? Chapter 11, Design of Steel Frames. 11.1 Braced versus Moment Frames. A braced frames, types, concentric braces, CBF, X, V, or K configurations, designed for axial forces only, eccentric braces, EBF, link beams for energy dissipation, seismic resistant design. Advantages, high stiffness for lateral loads, cost-effective for low to mid-rise buildings. Design considerations, slenderness ratio backslash left, backslash frac KLR backslash right, backslash lec 200 backslash, connection design for buckling prevention. B. Moment frames, types, ordinary moment frames, OMF, basic seismic resistance, intermediate moment frames, IMF, moderate ductility, special moment frames, SMF, high ductility for seismic zones. Advantages, architectural flexibility, open spaces, better energy dissipation in earthquakes. Design considerations, strong column weak beam concept, panel zone shear capacity comparison table, feature braced frames moment frames lateral stiffness high moderate construction cost lower higher seismic performance good, EBF better, excellent, SMF best. 11.2 Drift and stability considerations. A drift limits, ASCE 7, story drift, backslash delta underscore max backslash lec 0.02 H backslash, seismic, backslash delta underscore max backslash lec H slash 500 backslash, wind, P delta effects, secondary moments due to lateral displacement, stability coefficient backslash, theta lec 0.25 B stability analysis, effective length. Method, K factors for columns, direct analysis method, AISC AP7, notional loads for initial imperfections, reduce stiffness, 0.8 EI worked example, check drift for a 5-story braced frame under wind loads. 11.3 Diaphragm action. A types of diaphragms, rigid diaphragms, concrete slabs or thick steel decks, distribute loads uniformly, flexible diaphragms, thin metal decks or wood sheathing, load distribution varies. B design forces, shear transfer, /Q equals / frac VL /quad, text for uniform distribution, chord forces, T equals C equals frac M underscore max D /C connections, deck to beam welds or shear studs, collector elements for force transfer. 11.4 Practical applications. Case study 1, office building, braced core plus moment frames for mixed system. Case study 2, warehouse, rigid diaphragm with metal deck. 11.5 Common mistakes, braced frames, ignoring brace buckling out of plane, moment frames, overlooking panel zone deformation. Diaphragms, misclassifying rigidity. Chapter tools. Quick reference, parameter braced frame moment frame drift control stiffness ductility seismic design CBF/EBF SMF/IMF flowchart, frame system selection. Review questions. 1. Compare EBF versus CBF for seismic performance. 2. Calculate story drift for given wind loads. 3. Why are chord forces critical in diaphragms? Design exercises. Basic, select frame type for a 10-story building in seismic zone. Advanced, analyze P delta effects for a slender tower. Key features, visual aids, frame deformation animations, code alignment, ASCE 7/AISC 341 provisions, software links, tabs modeling examples suggested add-ons, video of frame testing, cyclic loading, Excel template for drift calculations. Would you like more on hybrid systems or performance-based design? Chapter 12, Floor Systems. 12.1 Composite Beam Design. A basic principles, effective width, /B_EFF equals /min /left, frac L4, B_slab /right, plastic stress distribution, full composite action, M_N equals F_YZ partial composite, reduced strength based on shear connectors. B shear connectors, AISCI3, stud capacity, /Q_N equals 0.5 A_SC /SQRT F_CE_C /LEC R_G_R_P A_SC stud cross-sectional area, R_G, R_P group and position factors. See deflection. Checks, construction stage, bare steel beam, composite stage, transformed section properties. Worked example, design a W16x31 composite beam with 3 concrete slab, F_C equals 30 MPa, 410 M span. 12.2 Open web steel joists. A standard joist series, SJI, series depth, in, span range, foot, load capacity, PSF, K10 to 30 20 to 60 40 to 200 LH 18 to 48 25 to 96 35 to 150 B design considerations. Virendial action, web member bending effects, bridging requirements, top chord lateral bracing every 10 to 12 feet. See special joists, joist girders, for heavy loads, e.g., mezzanines, seismic joists, diagonal web members. 12.3 Deck and slab interactions. A metal deck types profile rib height, in, concrete fill shear transfer -1.5 VLR 1.5 lightweight mechanical 3 and 3.0 normal weight. Frictional B composite action verification, slip capacity, \v_h equals \min, 0.85 f_ca_c, f_ya_s, deck anchorage, welded studs or puddle weld. C vibration control, natural frequency, target 8 Hz for offices, damping, use rubber pads for sensitive areas. 12.4 Practical applications. Case study 1, hospital floor, composite beams with 4 slab for vibration control. Case study 2, retail space, open web joists with exposed ceiling. 12.5 Common mistakes, composite beams. Ignoring shored versus unshored construction, joists, overlooking ponding effects, decks, misclassifying shear bond capacity. Chapter Tools. Quick reference, system span range, typical depth/span ratio. Composite beam 6-15 m1/18-1/22 open web joist 630 m1/20-1/24 flowchart, floor system selection. Review questions. 1. Calculate effective width for 8 m span with 3 m slab width. 2. Why are headed studs preferred over channels in composite beams? 3. Compare metal deck profiles for vibration sensitive areas. Design exercises. Basic, select joist series for 40 feet span with 100 psf live load. Advanced, optimize composite beam for minimum depth. Key features, detail drawings, composite beam cross sections, code alignment, AISC 360/SJI specifications, software links, composite beam design tools, suggested add-ons, video of composite beam load testing, Excel template for vibration analysis. Would you like more on post-tension slabs or fire-resistant designs? Chapter 13, Industrial Structures. 13.1 Crane runway girders. A load considerations, vertical loads, wheel loads, with impact factor equals 25%, P_max equals \frac crane \capacity 4 times 1.25 lateral loads, 10% of lifted load, side thrust, 20% of wheel load, longitudinal, B design checks. 1. Bending capacity, \phi_bm_n \gc_m_u \text, AISCF2, \2. Web crippling, \phi_r_n equals \phi 0.8t_w2 left 1 plus 3 left, \frac nd \right, \left, \frac t_wt_f right, 1.5 right f_yt_ft_w 3. Fatigue, category B. Details for welded connections /sqrt /frac ec. Practical details, rail alignment, tolerances less than or equal to 1/500 of span, impact mitigation, rubber pads under rails. Worked example, design a runway girder for 50-ton crane, wheel load equals 150 knots, span equals 8 m. 13.2 Storage rack design. A key standards, selective racks, AS4084, upright frame buckling considerations, beam to column connections, pushback racks, RMIMH 16.1, dynamic load factors. B load cases. Condition, vertical load, seismic load normal 100% inventory, seismic 25% inventory /f_p equals 0.4s_dsw C component design, perforated columns, effective area calculations, beam end connectors, moment rotation characteristics. Worked example, calculate seismic force for 5 m high rack, /s_ds equals 0.6 grams weight equals 20 kN/bay. 13.3 Transmission towers. A types. Type, height, range, typical load tangent 30-60 m wind and ice, dead end 50-100 m conductor tension. B load combinations, ASCE 74, 1. Normal, wind at 50-year return. 2. Extreme, wind at 500-year return plus broken wire. C member design, angle sections, slenderness ratio / lec 200 / connections, bolt slippage critical for vibration worked example, analyze leg member for 200 m span tower, wind load equals 3 kPa. 13.4 Practical Applications Case Study 1, Automotive Plant, 10-ton crane runway with welded box girders. Case Study 2, E-commerce warehouse, 1-2 m high pallet racks with seismic bracing. 13.5 Common mistakes, crane girders, ignoring lateral torsional buckling, racks, underestimating pallet impact forces, towers, neglecting ice load combinations. Chapter Tools Quick Reference, Structure Governing Code Critical Check Crane Runway CMAA Number 70 Web Crippling Storage Rack RMIMH 16.1 Upright Buckling Transmission ASCE 74 Wind Resonance Flowchart, Industrial Structure Selection Review Questions 1. Calculate wheel load for 75-ton crane, 4 wheels. 2. Why are perforated columns used in racks? 3. Compare tangent versus dead-end tower loads. Design exercises, basic, size runway girder for 5-ton overhead crane. Advanced, optimize lattice tower member sizes. Key features, detail drawings, typical industrial connections, code compliance, CMAA/RMI/ASCE standards, software links, PLSTOWR examples, suggested add-ons, video of crane runway fatigue testing, Excel template for rack seismic calculations. Would you like more on blast-resistant design or automated storage systems? Chapter 14, Plastic Design of Steel Structures. 14.1 Plastic Hinge Formation. A concept development, yield mechanism, /m_p equals f_yz plastic moment capacity, rotation capacity /theta_p /theta_y AISC 358, B stress strain progression 1. Elastic behavior, /m lec m_y 2. Yield penetration, /m ym lec m_p 3. Plastic hinge formation, m equals m_p C section requirements, compactness limits, \lambda_p equals 0.38 /sqrt frac ef_y quad, text flanges, \lambda_p equals 3.76 /sqrt frac ef_y quad, text webs, worked example, verify W18 times 50 compactness for plastic design, f_y equals 50 KSI. 14.2 Collapse mechanisms. A fundamental types mechanism beam condition hinge count beam mechanism simply supported one panel mechanism fixed 3 combined multi-span n+1 B virtual work method \/ sum m_p \theta equals \sum p delta upper bound theorem, smallest collapse load is correct. See worked example, determine collapse load for 2-span continuous beam, L equals 6 m, m_p equals 300 knm. 14.3 Ductility requirements. A material specifications, minimum elongation, 20%, A572 GR50, notch toughness, char PV greater than or equal to 20J at -20 degrees Celsius. B connection detailing 1. RBS connections, \0.5 B_F lec C lec 0.75 B_F AISC 358, /0.65 D lec A lec 0.85 D 2. Slab reinforcement, top rebars greater than or equal to 0.5% of slab area. C rotation capacity verification \theta_max equals 0.03 \text rad, SMF, 0.02 backslash text rad, IMF, backslash dash 14.4 practical applications case study 1, moment frame retrofit, RBS implementation in existing structure case study 2, industrial gantry, plastic design for overload protection dash 14.5 common mistakes, over-reliance on plasticity, ignoring stability checks, misapplied mechanisms, assuming wrong hinge pattern, ductility. Oversight, using non-ductile connections chapter tools quick reference, parameter SMF requirement IMF requirement backslash theta underscore P backslash, greater than or equal to 0.03 rad greater than or equal to 0.02 rad backslash lambda underscore P backslash, 90% of compact 100% of compact flowchart, plastic design process review questions 1. Calculate backslash, M underscore P backslash, for W21 times 62, backslash, Z underscore X equals 144 backslash, in superscript 3, backslash, F underscore Y equals 50 backslash, KSI. 2 sketch collapse mechanisms for 3-span beam. 3. Why is Charpy testing critical for plastic design? Design exercises, basic, verify hinge rotation for given backslash, M backslash theta backslash, curve. Advanced, optimize RBS dimensions for W24 times 94. Key features, failure animations, progressive hinge formation, code alignment, AISC 341 seismic provisions, software links, plastic analysis module suggested add-ons, video of cyclic hinge testing, Excel template for mechanism analysis. Would you like more on strain hardening effects or pushover analysis? Chapter 15, Seismic Design of Steel Structures 15.1 Ductile Detailing A Material Requirements, Steel Toughness, SMF, Charpy V notch greater than or equal to 20J at minus 30 degrees Celsius, AISC 341, CBF, greater than or equal to 27J at minus 20 degrees Celsius, yield to tensile ratio, backslash frac F underscore Y F underscore U backslash lec 0.85 backslash quad backslash text, prevents brittle fracture, backslash B critical regions 1. Panel zones, backslash V underscore U backslash lec backslash phi 0.6 F underscore Y D underscore CT underscore P backslash left, 1 plus backslash frac 3B underscore CFT underscore CF2D underscore BD underscore CT underscore P backslash right, backslash 2. Beam column connections, RBS, reduced beam section, radii cut requirements worked example, check panel zone shear for W24 times 94 beam to W14 times 120 column connection. 15.2 Special moment frames, SMF, A key provisions, AISC 341 CHE, strong column weak beam, backslash some M underscore PC backslash KIC 1.2 backslash some M underscore PB backslash, flange welding, CJP groove welds with toughness rated electrodes BRBS design parameters parameter AISC 358 limits cut location, A, backslash, 0.5 B underscore F backslash, to backslash, 0.75 B underscore F backslash, cut depth, C, backslash, 0.2 B underscore F backslash, to backslash, 0.25 B underscore F backslash, worked example, design RBS for W30 times 108 beam, backslash, B underscore F equals 10.5 backslash, D equals 29.8 backslash. 15.3 Concentrically braced frames, CBF, A system type slenderness, KL/R, brace angle SCBF less than or equal to 230 degree 60 degree OCBF less than or equal to 300 NEB buckling considerations, compression capacity, backslash phi P underscore N equals 0.9, 0.877 F underscore E, A underscore G backslash quad backslash text when backslash frac KLR 4.71 backslash SQRT backslash frac EF underscore Y backslash, gusset plate detailing, 2 tons linear clearance for rotation worked example, design HSS 6x6x 1/2 brace for 400 kip axial load, backslash, KL equals 12 backslash. Dash 15.4 Practical Applications Case Study 1, Hospital Retrofit, SMF Implementation with Viscous Dampers Case Study 2, Data Center, SCBF with Buckling Restrained Braces, BRBs, Dash 15.5 Common Mistakes, SMF, Neglecting Panel Zone Strength, CBF, Improper Gusset Plate Geometry, Material, Using Non-Sharpie Tested Steel Chapter Tools Quick Reference, System R Factor Height Limit SMF 8 Unlimited SCBF 6 160 OCBF 3.25 160 Flowchart, Seismic System Selection Review Questions 1. Calculate required backslash, M underscore PC backslash, for W14 times 132 columns framing W24 times 76 beams. 2 YR 30 degrees brace angles preferred in CBF. 3 Compare SCBF versus BRB energy dissipation. Design exercises, basic, size gusset plate for HSS brace, AISC 341 CHF. Advanced, perform pushover analysis for SMF. Key features, failure animations, brace buckling versus yielding, code compliance, AISC 341 to 22 updates, software links, OpenSeas model suggested add-ons, video of cyclic connection tests, Excel template for RBS design. Would you like more on base isolation or performance-based design? Chapter 16, Cold Formed Steel Design 16.1 Light Gauge Sections. A manufacturing process, roll forming, 18 to 24 gauge steel, 0.018 0.075, material properties, backslash, F underscore Y equals 33 to 70 backslash, KSI, ASTM A1003, increased backslash, F underscore Y backslash, at corners, cold work effect, B section types profile applications advantages C section wall studs, floor joists high torsional rigidity Z section roof purlins nesting capability. Track section headers / runners easy assembly C local buckling, effective width method, AISIS 100 \B underscore E equals \, begin cases W and \, text if \, lambda \, lec 0.673 \, W left, frac 0.22 lambda, frac 0.8 lambda 2 right, and text if lambda 0.673 end cases where lambda equals sqrt frac f underscore y f underscore cr worked example, calculate effective width for 6 flange with t equals 0.045 f underscore y equals 50 KSI-16.2 wall stud design. A axial capacity, AISIS 240, 1. Global buckling, \P underscore N equals F underscore NA underscore E quad, F underscore N text from AISIE 3, \2. Distortional buckling, \F underscore D equals frac pi 2E, KL, underscore D2 B. Practical details, typical spacing, 16 or 24 OC, sheathing contribution, increases buckling capacity by 30 to 50%. Worked example, design 10 feet high stud wall with 550 lb foot load, with OSB sheathing. 16.3 Diaphragm action. A steel deck diaphragms, shear capacity, \V underscore N equals min begin cases text deck strength text fastener strength text boundary element strength end cases stiffness, G equals frac G1 plus 0.0025, SDR, B design tables, AISID 310, deck type bare steel capacity, PLF, composite capacity, PLF, dash 22 gauge 300 820 gauge 451,200 worked example. Determine diaphragm capacity for 1.5 VLR20 deck with number 10 screws at 60C-16.4 Practical Applications Case Study 1, Mid-Rise Residential, CFS Load-Bearing Walls with Composite Floors Case Study 2, Warehouse, Z-Purlin Roof with Steel Deck Diaphragm 16.5 Common Mistakes, Connection Detailing, Underestimating Screw Fatigue, Bracing, Ignoring Torsional Effects in Z-Sections, Corrosion, Unprotected Cuts in Coastal Areas Chapter Tools Quick Reference, Component Governing. Standard Key Check Studs AISIS 240 Distortional Buckling Diaphragms AISID 310 Fastener Slip Flowchart, CFS Design Process Review Questions 1. Calculate distortional buckling stress for 600 S162-54 stud. 2. Why are Z-sections preferred for purlins? 3. Compare bare versus composite diaphragm performance. Design exercises. Basic, select stud spacing for 40 psf wind load. Advanced, optimize deck screw pattern for seismic loads. Key features, detail drawings, typical CFS connections, code alignment, AISIS 100-16 updates, software links, CFS design tool suggested add-ons, video of diaphragm testing, BIM models for CFS assemblies. Would you like more on modular construction or fire-rated assemblies? Chapter 17, Sustainability in Steel Design 17.1 Recyclability of Steel. A circular economy benefits, recycling rate, 90% plus of structural steel is recycled, AISC, embodied energy, recycled steel uses 75% less energy than virgin production, closed-loop systems, beam and LCA tool for tracking recycled content. B design for disassembly, bolted connections, preferred over welded for easier deconstruction, standardized components, facilitates reuse in other projects worked. Example, compare. Embodied carbon for AW 12x30 beam, virgin versus 80% recycled content. 17.2 Life Cycle Assessment, LCA, A Key Phases, ISO 14040, 1. Material Production, GWP, 1.8 to 2.5 kg CO/kg steel, electric arc furnace, 2. Construction, 5 to 15% of total impact. 3. End of life, credit for recyclability, minus 0.5 to minus 1.0 kg CO/kg, B Tools and Standards Tool Region Key Feature Athena Impact Estimator North America AISC Certified Database eTool Global N15804 Compliance Worked Example, Conduct Cradle to Gate LCA for a 10-ton steel frame. 17.3 Modular Construction. A Steel Advantages, Precision, plus or minus 2 mm fabrication tolerances, speed, 30 to 50% faster than conventional construction. B Connection Innovations. 1. Intermodule connections, proprietary seismic resistance systems. 2. Vertical stacking, capacity designed shear keys. Case study, 50-story modular tower, 95% prefabrication, 70% reduced site waste. 17.4 Practical Applications. A LEED/BREEAM credits, Mr. Credit 4, recycled content, 1 to 2 points, ID Credit 1, Innovation in Modular Design. B Carbon Reduction Strategies, High Strength Steel, 20 to 30% weight savings, Hybrid Systems, Steelwood Composites. 17.5 Common Mistakes, LCA Boundaries, excluding transportation impacts, modular detailing, ignoring tolerance accumulation, recycling claims, assuming 100% recoverability. Chapter Tools Quick Reference, Strategy CO reduction potential -90% recycled content 60 to 70% modular construction 15 to 25% flowchart, sustainable design decision tree -review questions 1. Calculate CO savings using EAF steel, 2.1 kg CO/kg, versus BOF, 2.8 kg CO/kg. 2. Why are pinned connections better for circular economy? 3. Compare modular versus conventional construction schedules. Design exercises. Basic, optimize a beam for minimum embodied carbon. Advanced, develop DFD, design for disassembly, details. Key features, case studies, net zero steel buildings, regulatory alignment, EU taxonomy/IGBC criteria, digital tools, Tally Revit plugin demonstration suggested add-ons, video of modular steel erection, Excel template for carbon calculations. Would you like more on low carbon alloys or deconstruction case studies? Appendices. Appendix A, Steel Section Properties. A. Standard rolled sections, AISC Manual, Section Weight, lb/foot, Area, in superscript 2, 9, in, ZX, in superscript 3, W12 times 50 14.6 391 64.7 HSS 6 times 6 times 1 half 22.5 6.63 28.6 11.2 C 12 times 30 38.82 162 33.0 B metric equivalents, and 10,210, section mass, kg/m, area, cm superscript 2, e, cm, He 242.353.8 3690 SHS 150 times 522.7 28.9 1080 Appendix B, Design Aids and Charts. A beam selection chart, x-axis, unbraced length, foot, y-axis, available moment, kip ft, curves, for W12, W14, W16 series B column strength curves, backslash phi p underscore n backslash, versus backslash, KL/R backslash, 4A992 steel C connection coefficients, bolt group backslash, C backslash, factors for eccentric loading Appendix C, connection design tables. A. Bolt capacities, bolt size, single shear, kips, bearing, kip/in. -3/4 A325 N 15.987.01 A490 X 31.8 154 B weld strengths, weld size, in, capacity, kip/in, -1/4 E70XX 4.181 half E70XX 8.35 Appendix D, example problems with solutions. Problem 1, given, W18 times 35 beam, 30 feet span, uniform load 2 kip/foot, find, check adequacy for bending, AISC LRFD, solution, \m underscore u equals \frac WL28 equals 225 text kip ft phi. M underscore n equals 0.9 times 50 times 66.5 equals 299 text kip ft 225 text problem 2, given, HSS 6 times 6 times 1/4 column, KL equals 12 feet, find, axial capacity, AISC ASD, solution, \frac KLR equals 55 right arrow F underscore CR equals 36.7 text KSI P underscore N / omega equals \frac 36.7 times 5.24 1.67 equals 115 text kips -- references and further reading. A standards and codes 1. AISC 360-22, Specification for Structural Steel Buildings 2. AISIS 100-16, North American Specification for Cold Formed Steel 3. And January 1, 1993, Eurocode 3, Design of Steel Structures B Textbooks 1. Salmon, C.G., et.al., 2009. Steel Structures, Design and Behavior 2. Traher, N.S., 2018. Behavior and Design of Steel Structures C Digital Resources 1. AISC Design Tools, www.ac.org/design-tools, https://www.isc.org/design-tools, 2. MIT OpenCourseWare, Steel Structures Design D Research Papers 1. Ewan and Fan, 2001. Cyclic Testing of RBS Connections 2. Schaefer and Pecos, 1998. Cold-formed steel behavior - key features ready reference, quick lookup for 50-plus standard section solved examples, step-by-step design verification code aligned, updated to 2022 standards suggested add-ons, interactive section property calculator, Excel templates for beam/column design. Would you like additional example problems or BIM integration tips? Here's a refined version of your textbook's pedagogical features with enhanced organization and actionable details, pedagogical framework and customization guide. Core features 1. Dual code compliance, AISC 360-22, full LRFD/ASD implementation with side-by-side equation comparisons, e.g., phi pn versus pn/omega, US customary unit case studies, Eurocode 3, key differences highlighted, partial safety factors, gamma m0 equals 1.0 versus phi equals 0.9, metric unit worked examples 2. Practical implementation, case study library, project type key learning objective visual aid -40 story SMF tower seismic connection detailing erection sequencing videos automotive plant crane runway vibration analysis strain gauge field data, construction photos, annotated images of typical weld defects, buckling failure case studies 3. Innovation modules, BIM integration, LOD 400 modeling standards, Tekla/Revit workflow diagrams, circular economy, material passports case study, DFD, design for disassembly, connection details discipline-specific customization a civil engineering focus, enhanced content, Chapter 11 expansion, add mixed steel concrete systems, include seismic retrofit techniques, new case study, stadium roof design, large span trusses, B mechanical engineering focus, additional modules. Vibration analysis of equipment supports, API 610 baseplate design, fatigue life calculations, Miner's rule, high temperature design, creep effects on steel frames, expansion joint detailing C global market adaptation, dual standard implementation, comparison tables, design aspect AISC 360 Eurocode 3 - beam lateral bracing LP equals 1.76 Re, E/phi, LCR equals pi, EI/GJ, regional case studies, US. High seismic SMF with RBS, EU, wind dominant moment frames per N January 4, 1991 instructional support package, digital resources, for professors, lecture slides with toggleable US/EU standards, auto-graded connection design problems, for students, AR app for steel section visualization, Python scripts for, bolt group analysis, deflection calculations, assessment tools, basic, standard code check problems, AISC/Eurocode options, advanced, open-ended design challenges, e.g. Optimize a warehouse portal frame, suggested customization workflow 1. Select core audience, civil mechanical global 2. Choose emphasis, seismic sustainability digital workflows 3. Specify delivery format, print and digital interactive ebook example adaptation, for a global sustainability focus, add comparative LCA, US versus EU steel production, include modular bridge case study, UK DFMA standards, integrate digital material logs using IFC 4.3. Would you like me to develop specific learning objectives for any of these custom tracks?